Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to our virtual lecture. Today, I would like to start chapter 4, chemical reaction and chemical quantities. As usual, I will share my screen so that you can see my whiteboard. Right now, I do have a PowerPoint slide on the left side of the screen and the whiteboard on the right side of your screen. As usual, the chapter will be divided into two sections, part A and part B. In part A, I'll cover section 4.1, 4.2, 4.3, and I'll come back again to cover part P 4.4 and 4.5. Make sure that you come back or you go and watch part B of the lecture recording. To start off part A, section 4.1, climate change. I know this term you have heard over and over again, climate change. Some folks use global warming and stuff like that. What does it have to do with chemistry? As far as we are concerned, why do we have to, what is the connection between our chapter and climate change? Just to give you an understanding of what climate change, or this has to do with the concentration of carbon dioxide in the atmosphere. Maybe I can just blow up this for full screen so that you can see the diagram representing the Earth, greenhouse gases. You know, greenhouse gases release carbon dioxide, and carbon dioxide form a layer of the atmosphere, and this will act as a one-way, all right, traffic or way for the sunlight to enter the atmosphere, but it cannot go, or the Earth cannot radiate back the heat from the sun. This represents the heat from the sun, and because of the greenhouse gases, it cannot go back, or it cannot be radiated back to the atmosphere. This has been argued that it increases the temperature of our planet. So the balance between the incoming and the outgoing energy from the sun determines the average temperature of the Earth, hence the term climate change, global warming. And in around mid-18th century to 2020, this is the concentration of the carbon dioxide. And in comparison with the global temperature since 1880 to 2020, you see there is exponential increase in temperature, which relates to the carbon dioxide concentration in the atmosphere. All right. Scientists have argued out that an average of 0.7 degrees Celsius rise in atmospheric temperature since around 1880. During this same period, there is an increase of about 38% CO2 on the atmosphere. What is the relationship between the two? And where is the source of CO2? Okay. Now, one school of thought argues that the source of CO2, which causes the increase in temperature, has to do with the combustion reaction of fossil. In other words, one school of thought is arguing that one source of CO2 is from the combustion, burning of fossil fuel, all right, with oxygen. And this has to do with what we always use in our homes, in gasoline and so forth. The other school of thought argues that the source of CO2 is the volcanic action, that due to eruption of active volcano, the increase, the two temperatures. I want you to look at this and this, that one school of thought is arguing that the concentration, the increase in this concentration, which leads to increase in temperature, has to do with either combustion, and some are arguing that it has to do with the volcanic. So if I ask you, which one will you, do you think? Is it increase in CO2 is related to the fossil fuel, or is it as a result of CO2 from the volcanic action? How can we judge whether the global warming is natural? Natural means it's from volcanic action or due to activities, that's the combustion reaction of fuel. Well, we'll see later on. Hold on to that question. We'll see how do we really determine whether it is as a result of nature or whether it is as a result of use of fossil fuel in combustion. In the meantime, let's just dive into the concept you already know from intro to chemistry, writing and balancing chemical equation, writing and balancing chemical equation. Scientists use, scientists use chemical equation to represent chemical reaction, all right? For example, chemical reaction, see, whiteboard. Trying to see my whiteboard. It's working. It's not working. I'm just gonna make sure. Yes, let's see. My whiteboard, yeah, it's working now. We are back on business. So chemical reaction is represented by chemical equation. For example, here is the reaction between hydrogen gas and nitrogen gas to form ammonia. This is a chemical equation representing a chemical reaction between hydrogen gas and nitrogen gas. In section 4.2, we will look at how to balance the equation. Why do we need to balance the equation? Because of the law of mass conservation, which states that matter cannot be created or destroyed. That is the essence of balancing the equation. For example, if you look on my example here, I have two hydrogens on the left side of the reaction arrow. I have three on the right side, on the product side. The equation is not balanced. This equation is not balanced the way it is. And balancing the equation is simply using what we call coefficient. Coefficient is a digit which goes in front of a reactant on the left side, and products on the right side. I know you know how to interpret the chemical equation or reaction. So we need to put a 2 in front of ammonia gas, and this will change the number of nitrogens on the right side, on the product side. We read this as 2 nitrogens and 3 times 2 hydrogens. So this, we have 2 nitrogens and 6 hydrogens. That's how you look at the product side. On the reactant side, there are 2 nitrogens. Even though you don't see anything here, there is one. It's understood that there is one there. So the nitrogens, you can use a check mark to say this is balanced, this is balanced. But if you look at the number of hydrogens, 6 versus 2, this is interpreted as 2 hydrogen. How do we make it equals on the left side? Is by, all right, is by using the coefficient 3 here to balance the equation. We say the equation is balanced. This is 2 times 3 hydrogens, 6. So this is 6 hydrogens, 6 hydrogens two nitrogens. Even though there is nothing here, it's understood that there is one there. Don't think that it is zero. No, there is two. So what I've done here, I've balanced the equation, and that's all you need to remember. There is no equation for balancing the chemical equation. There is no formula for balancing the equation, except you need to learn the guidelines for balancing the equation. So what is a chemical reaction? I've just explained that. It describes the hypothesis, arrangement of atoms in a chemical reaction. So what I want you to know is we use chemical symbols to denote what occurs in a chemical reaction. It's chemical equation here. This is interpreted as two moles, by the way, 2 moles of hydrogen react with 1 mole of nitrogen to form 2 moles of ammonia. So you interpret, we'll come back to that later. I know you know what how to interpret a chemical equation. On the right side of the reaction arrow, we call these reactants. Sometimes reagents, all right, we call reagents. It means the same thing, or reactant. It's the same thing. Sometimes we can interchangeably use the two terms. You need to know the what it means, formulas for the reactant. Let me go back here. Formulas of the reactant and product. These are the formulas. Remember, in the previous chapter, we learned how to write the correct formulas for elements. We talk about the atomic molecules, such as hydrogen here. There is nitrogen. And we learn how to write the correct formulas for molecular compounds, a non-metal and a non-metal. Remember, this is where you need to be well-rounded in writing the names, all right, for your compounds or elements. State of the reagents. States here, you will see here I've used G. This means it's in gaseous state. This is in gaseous state. This is in gaseous state. Sometimes we use other states such as S. This means it is in solid state, all right, solid state. L, this means it is in liquid, liquid state. And this means AQ means aqueous. It means dissolved in H2O. This means dissolved in H2O. So if you dissolve sodium chloride in liquid H2O, you will see a notation, or if you see something like that, this is table salt dissolved in water. But NaCl, this is just the regular table salt. It's in solid state. So remember, the states here has to do with liquid, and of course there is gas here. You need to know this means it is in gaseous. What is in gaseous state? You'll see that again. All right. So remember, the coefficient in front of each one of these compounds or elements indicate the relative number of the reactants. All right, we'll see that. So here are the states you need to remember. Liquid, L, G for gas, solid means aqueous, dissolved in water. You'll see this throughout the course, and beyond, you need to understand what it means, So here are just few examples. I know you can go through in the PowerPoint slide. You should be able to interpret. Look at ammonia react with HCl to form ammonium chloride. Here is by now you should be able to interpret a chemical equation using the names. Ammonia, we learned earlier on, hydrogen chloride, HCl. You see this hydrogen chloride react to produce ammonium chloride. Sometimes you may see This means to produce an arrow. Let me just here so that you see other ways of this means right here. This means react with, all right. It can be combined with, all right. It means react with, combine with. The arrow means to yield, can be mean to yield, to produce, to give. It's the same thing. So you'll be given a worded chemical equation, and you may see this. Sometimes you may see a symbol above the arrow, means heat is required. Heat is required. It can be a catalyst, such as this, means iron is a catalyst. You know what a catalyst is? A species that speeds up the reaction but does not participate in the formation of the product, does not participate in the chemical reaction. This means iron is a catalyst. So just to give you, some of the symbols you may see in a chemical equation, you should be able to interpret. Here is another example on how to interpret a chemical equation. This is sulfur trioxide. You read this as sulfur trioxide react with water to produce sulfuric acid, So on the left side of the reaction arrow, we call those reactants. On the right side, we have the product. Sulfuric acid is our product in this equation. So remember from this slide here, the product and the reagent where they stand. Now, physical state in the previous slide, these are just, the physical state of the reagent. This means they are in gaseous state. This is in solid state, gaseous state, and so forth. It's pretty straightforward. Balancing the equation I've given you before. An example on how to balance the equation. What I want you to see here is liquid H2O is produced when gaseous H2O react with gaseous hydrogen. Remember, in nature, hydrogen is in diatomic. All right. This is balanced so that the chemical equation is balanced. We need a coefficient in front, balancing in front. Remember not to change the subscript when balancing the equation. What do I mean by that? Let's say if you have a hydrogen gas reacting with oxygen gas to produce liquid H2O, do not change the subscript. In other words, you cannot say, let me put a 2 there, so that you have 2 oxygen. Never change the subscript. Only the coefficients are used. This is peroxide. If you change the subscript, you'll end up with a different compound altogether, not what you intend. From here, we wanted to balance out the reaction between hydrogen gas and nitrogen gas to produce liquid H2O. So we need 2 here, we need 2 there, and we say the equation is balanced. Perhaps maybe fast forward to guidelines for balancing the equation. Remember that, as I said, there is no formula. It is just trial and error approach by just using numbers in front of a reactant or reagents and in front of a product or products. in such a way that all atoms on either side of the reaction are sub. Here are just general guideline which might help you with practice. It will, with practice, it will help you changing the coefficient of a compound before changing the coefficient of an element. So it's just trial and error. I don't want to say memorize this, polyatomic ion, you can treat as if it is a single unit. Let me just show you how you can treat polyatomic ion. Let's say, for example, here, if I say lead to, let's practice with this, lead to nitrate, and it is aqueous plus potassium, all right, potassium chloride, chloride, IDE, chloride to produce potassium, or I can start with lead 2 chloride, lead 2 chloride solid. This is aqueous, by the way, plus potassium nitrate. Potassium nitrate. So this is awarded chemical equation. I'm just giving you or raising a red flag that you should be able to translate awarded chemical equation to formulas, and then you balance. That's what we are doing right now. So here you will see that lead 2 nitrate is PP NO3, and it is subscript 2. Remember how to write the formula, and this is aqueous plus KCl aqueous, and the formula here for, by the way, this is an arrow, I meant to say produce PPCl2 plus, this is solid, plus KNO3 aqueous. This rule number 2, treat polyatomic ion that appears on both sides of the equation, e.g. carbonate. It's not only always carbonate, but here we are looking at nitrate. If you look at the nitrate here and the nitrate here, you treat as if it is a single unit. So I read this as 2 nitrates, 2 times 1 nitrate, 2 nitrates here, all right? I'll say 2 nitrate, and remember the formula for nitrate is NO3 subscript and negative. Here there is 1 nitrate here, NO3 with a negative, NO3 with a negative. We need to balance this. This is now when you treat it as if it is a single unit, that you need a 2 in front here so that it balances the nitrate. So I have 2 nitrates right here. And the 2 nitrates, and the equation is balanced. The equation is balanced. Chloride, we have 2 here. There are 2 chloride. We have 1 here, so I need a 2 in front here, and the equation is balanced the way it is. What I've done is I've just treated nitrate as if it is a single unit. Do not just split it into oxygen, nitrogen, split it into oxygen, nitrogen. Yes, you can do that, but that it will take a long time before you get the right coefficient. And here, I'll say that 1 here, all right, we have 1 layer there, and the equation is balanced. The equation is balanced. Just practice when you see polyatomic ion on either side of the reaction arrow, treat it as if it is 1. Count atoms or polyatomic ions carefully and track the numbers. It's just common sense. Here are just few, examples I have on the PowerPoint slide, which I expect you to practice with it. Butane, this is butane. Remember in section 3.11 in chapter 3, organic compounds, naming organic compounds. This is butane, hydrocarbon, combustion with oxygen. You have to go back and forth until it balances. All the numbers here is just, it depends on which one works best for you. You can start balancing carbon, you can start balancing oxygen, but remember rule number 1, you just leave the element by itself so that you balance at the end. So this is just the next slide. Sometimes you may use fractions so that you multiply by 2. So if I multiply by 2 here, multiply by 2 here, multiply by 2, multiply by 2. Remember, we don't use fraction. For example, if I divide this by 2, I'll get 6.5. No, we don't want that. So you multiply across by 2, by 2, by 2, by 2, so that this equation in the long run look like this, so as to eliminate the fraction. Don't want to say what happened with the 2 which was in front of oxygen, just multiplying it across, and do the accounting at the end. Make sure that the atoms on either side adds up, right? Here, this is an example of reaction between barium hydroxide and perchloric acid. Have underlined or have bolded the barium hydroxide and perchloric acid just to let you know that you need to apply what you learned in the previous chapter. Naming of the compounds, you should be well-grounded in that. Barium hydroxide, how do I know that this is barium hydroxide? You know, I don't want you to think that barium hydroxide is PaOH. Somebody will think that, why don't I just have that? No, you need to understand that hydroxide is negative and barium is in group 2, so it has a charge of -2. And remember the crossover rule, Pa 2 positive and OH negative. The -1 positive 2 there, we'll end up with PaOH2. You need to be able to write the correct formulas. Don't memorize. In other words, don't think that I'll ask you exact same question you see here. Perchloric acid, remember binary acid, oxy acid, this was one of the oxy acid, and exchanging of ions to produce liquid H2O, you should be able to write barium perchlorate and water. By the way, the chlorate ion has a charge of -1. So here ClO4, this is chlorate, perchlorate. This is perchlorate. Chlorate water, chlorate ion. It's a polyatomic ion, and barium is in group 2. We end up with that. So if you look at this, we have only one perchlorate ion. Here we have two. Here, this is what we talk about, treating the polyatomic ion as if it is a single unit. So here it's just going back and forth until you end up with the correct number of the coefficient in front of each reagent and product, so that the equations balance out and we are using the correct. So here, this is the, if you look at this one barium, this 2 applies to hydrogen, applies to perchlorate ion here. So 2 perchlorate and 2 perchlorate. If you look at hydrogen, there are 2 hydrogens, 1 hydrogen times 2, so 2 plus 2 is 4. Remember to add on either side, that is why 4, 4. All right, 2, 2. The numbers here indicates that barium on either side, this is reaction arrow on the reactant side, on the product side. And the coefficient is 1, 2, 1, and 2. That is an example. Another example is combustion of, or not combustion, but metabolism of butyric acid, which is just like combustion. You need to balance the equation. This is the formula for butyric acid, right? Just the way we did before, you have to go back and forth until you get the correct coefficient in front of the reactant or reagents and product. Here, you'll see 4 hydrogens. Maybe I can just have this big. If you look for carbons, 4 times 1, 8 hydrogens, and 4 times 2 is 8 hydrogens. Look at the oxygen. This is how you account for oxygen. We have 2 here plus 10. 2 times 5 is 10, so 12. So here is 4 times 2 is 8 plus 4. 4 times 1 is 4. So 12 oxygens on either side of the reaction are. Well, you see most problems at the end of the chapter think about combustion. Combustion is burning in oxygen. And methane, by the way, you should be able to write the formula for that. Methane is CH4. So if we have that CH4, this is methane, by the way. This is methane. If you don't know what methane is, you'll be at a loss. Methane gas burns to produce, and when we say burns, that means it's in oxygen. So if I have CH4, this is gas, the natural gas, plus oxygen, which is the atomic energy, to produce what? To produce carbon dioxide. You should be able to write the formula for carbon dioxide plus calcium, H2O. So this means it will be H2O. It's not always that water is in liquid state. So let's balance the equation. If I am to balance this, I'll read this as one carbon. One carbon is okay. How many hydrogens? This 4 hydrogen. We have 2 here. Let me just put a 2 in front here to balance the what? To balance the hydrogen. So hydrogens are balanced out. I'll use a check mark. You see a check mark? This is a check mark. See my check mark right there. Oxygens. 2 plus 2 is 4. So I need a 2 in front here. And there is a 1 there. There is a 1 there. You can just leave that. And the equation is balanced away. So if you look at how I approach this problem, I had to write the correct formula for my compounds. Or here we only have one reagent, one reactant, methane. If I didn't know the formula for methane, and then how will I balance the equation? I cannot stress more the importance of writing the correct formulas for your compounds. Otherwise, you will get stuck. You will be a non-starter in writing or in balancing the equation. If you cannot write the formulas, you cannot balance the equation. So this is what I just did. And we balance the equation by adding the oxygens. If you look at that, and finally the equation, you see we need 2 hydrogens. We have to balance. So here is the balanced equation. By the way, chemists use color coding to represent our atoms. The white sphere, if you recall from intro to chem, if you took intro to chem last semester or this semester or any other time, the white sphere represent hydrogen, the black one represent carbon and oxygen, just to give you models. If you want to practice on, this is just, if you want to practice on balancing the equation, look at problems 13, 15, 17, 19, 21, 23, 27 on page 160 and 161 in the text, all right? Before we move on, let's see, write a balanced equation, write a balanced equation when propane should be propane react with oxygen gas. So here, propane, again, section 3.11, this was the last chapter, organic compound propane. You should be able to write the correct formula for propane, all right? Propane is CH38, or you cannot see, let me just minimize that. So this is the formula for propane, or in other words, 3 carbon chain with hydrogen, 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 hydrogen. So we have 8 hydrogens in propane. And this is the formula for propane. So that is the chemical formula, H8, could be gas, right? Plus oxygen gas, by the way, nitrogen gas, hydrogen gas, fluorine gas, and bromine liquid. Those are, or oxygen gas in this case, they are the atomic energy to produce. You know, hydrocarbon always produce CO2. It's assumed that you know combustion. CO2 plus H2O. This is calcium. Sometimes you may not be given the product. I mean, you are wondering why we have not been given the names of the product. Expect you are expected to know that combustion of hydrocarbons always give you CO2 and H2O. This is hydrocarbon, by the way. Carbon, that means it has carbon and oxygen in it, and when they combust, give you CO2, and this is gaseous state, and we are expected to balance this, write a balanced equation. So I'll start with carbon here and say, I have 3, we have 1 here. Let me just try and put a 3 in front of CO2 so that carbon and carbon is just trial and error. Here, A, hydrogens, we have 2 here. So I need a 4 to balance out hydrogens. Let's see. And then oxygen here, I'll just leave this one to be the last and just do the product side. 3 times 2 is 6, plus 4 is 10. You see what I'm doing? 3 times 2 is 6, all right? 6 plus 4 equals to 10. You ask yourself, what do you need to multiply by these two to give you 10 on the product side? And it turns out to be 5. It's just common sense. Everybody knows that 5 times 2 is 10. So the equation is balanced the way it is. This is the reaction or combustion of propane or reaction of propane with oxygen gas. Like I said, please practice with this end of chapter problem. If you look at this, they are all problems. There are answers at the back of the word. There are answers at the back of the book. So please remember that. Let's see, back to our question. Remember the question about the global warming, all right? The question about the global warming. One school of thought argued that, or is arguing that, global warming is as a result of burning of fossil fuel. Other school of thought is arguing that it is as a result of our active volcano. How do we know? It is by using reaction stoichiometry. And what is stoichiometry? Stoichion, coming from the Greek term stoichion. Here stoichiometry, stoichiometry. I'll just simplify this as quantitative relationship between products and reagents or reactants in chemical equation. This is the definition of just in simple terms, definition of stoichiometry. How my carbon dioxide? This question, how my carbon dioxide is, how do we quantify the amount of carbon dioxide given off when certain amount of fossil fuel is burned? This is octane. We are all familiar with octane, all right, the gasoline. Using this equation, which is balanced, all right, this is a balanced equation between reaction between oxygen, that's combustion of fossil fuel, octane. Notice the numbers in front of the reagent. It represents number of moles or molecules. So you read this as for every 16 moles or molecules of CO2 are produced when 2 molecules of octane are produced. You see, this is a lot. If 2 produce 16, this is responsible for global warming. The CO2, you can imagine if we had a lot, like in columns, it will be so much. So in a chemical reaction, for every amount of substance used and made in a chemical reaction, it relates to the amount of all other substances in the reaction. Remember the law of mass conservation, matter cannot be created or destroyed. So we need a balanced equation in order to abide by the law of mass conservation. The numerical relationship, remember I described the stoichiometry, it is the quantitative relationship between the product and the reagent. We're looking at in terms of moles. So you read this as 2 moles of octane react with 25 moles of oxygen to produce 16 moles of carbon dioxide and 18 moles of H2O. I want you to take note of the coefficient in the balanced equation. We do not write as plus, or we do not write as equals to. I know in math, 2 plus 2 equals to 4, but the mole ratio, this is called the mole ratio. You understand here, this is called mole ratio, mole ratio. Not rations, but ratio. So if I have N2 plus H2 to produce, this is gas right here, this is gas right here, and NH3 gas for ammonia, the 2, 3, and the 1 here. It's not 1 plus, all right? Mole ratio is 1 to 3 to 2. That's how you read. You say 1 to 3 to 2 is for ammonia gas, for hydrogen gas, for nitrogen gas. So likewise here on the PowerPoint slide, you see 2 is for octane, 25 is for oxygen, 16 is for carbon dioxide, and 18 moles for H2O. That's what the coefficient in the balanced equation. It's not in grams. You don't say 2 grams react with 25 grams. No. It's just mole ratio. So we will be using the coefficient in the balanced equation to do what we call conversion, to see how much of a product will be produced when you have certain amount of reagent. For example, making a pizza, if you say to make 1 pizza, you need 1 plus 5 ounces of tomato sauce, 2 cups of cheese to make 1 cup, not to make 1 pizza. If we have, right, 6 cups of cheese, how much or how many pizzas will be produced? We just use the ratio. Likewise, we use the moles. By the way, there are 2 or 3 or so types of calculation you need to remember. Types of calculation. Stoichiometric calculation. what you see here is there is mole to mole. That means you are given certain moles of a reagent, how many moles of a product will be produced, or if you have this reagent, how many moles of reactant A will react with certain moles of reactant B. There is mole to mole, and then there is mole to mass. It's the same as mass to mole. It's the same thing. You need also to learn mass to mass to mass. The longest one is the last one. The first one is the easiest, all right? On the PowerPoint slide here, it falls under mole to mole. There is the mole to mole conversion. Here, 2 moles react between 5 moles to produce 16 moles. And in these examples, stoichiometric ratio. All right, 2 moles of octane react with. We can be asked any question. For example, suppose we burn 22 moles of octane. How many moles of CO2 will be produced? It's very simple. You see this? It's the mole ratio, 22. You always cancel, set up your calculation so that you cancel out the, as if you are canceling the units, 20 multiply you have 176, which means combustion of 22 point, and by the way, this means 3 significant figures. You may have more than 3, please pay attention to. So this is how much CO2 will be released to the atmosphere. You can convert to grams if you want to using the molar mass of CO2, which I know you can find out, right? You can find out from that. Now, use the balanced equation for the combustion of octane to determine how many moles of, it's very easy for this. You need to set up, let me just minimize this, probably you look at this right here. Use the balanced equation. Sometimes you may be required to balance the equation first before you do the calculation, but already it is balanced for you. All right, to determine how many moles of are produced combustion of 22 moles. So how will you set up that? This is the setup. Look at what you are given. 22. And there is a reason why we have 0 here. It means 3 significant figures. And moles of what? Moles of C8, H what? H18. All right. H18 times, we want to get rid of moles of what? Moles of C8, H18. See how I'm setting up? And I'm looking for moles of what? Moles of H2O. Moles of H2O. Read the question again, how many moles of H2O? So moles of H2O, this is what we need to pay attention. Mole ratio between octane and H2O is in gaseous state is 18. So you just plug in the numbers here, 18 for every 2 molecules of methane consumed. This will go away, this will go away, this will be none. You multiply and then maintain the number of significant figures and include the units, all right? Moles of H2O. Don't just say 198, by the way. Don't just say 198. And here, these are the problems you can practice with. This is what I've, just try to bring the youth that if you want to practice with this, sometimes I just give you an example and you don't go back. You're like, okay, and then you read only the PowerPoint slide or watch the recording and say, I was making my own notes. I want you to go back to end of chapter problems. These are odd numbered problems and you should have answers to the back. Double check. This is a good practice for you. All right. Mass to mass, I just given you type of stoichiometric, which you need to know. That means you are starting with mass of a reagent, and you are asked, what is the mass of the product? Going back to global warming, the world burned an equivalent of 3.7 times 10 to per 10 parts of petroleum in 2017. By the way, this is a hydrocarbon, which means it releases CO2, which is responsible for global warming, global change. And in mass to mass, what I've highlighted here, that means we are starting with mass A, in this case, the hydrocarbon, the fossil fuel. Using the formula for hydrocarbon, we can convert to moles of hydrocarbon. And then we now determine the number of moles of CO2 in this case using the mole ratio in the balanced equation. And then we convert to mass of CO2. This is mass to mass. Simply, this is a roadmap, okay? It's not an equation, but it's a roadmap you can practice until you commit to your memory on how to do the mass to mass conversion or stoichiometry. We use the molar mass as a conversion factor to move from here to here. Please, if you don't know how to find the molar mass using the periodic table, that means you still need to go back and do some remedial work on finding the molar mass of a compound. You will not be in a position to find the molar mass unless you write the correct formulas for your reagents. It's the same thing for our product again, and use that as a conversion factor. All right, in this case, this is octane, the fossil fuel being mentioned here. We can convert to moles if you look at moles. And by the way, this setup right here, let me just show you how this works so that you can double check the numbers we have here. This is the balanced equation. We need, if we burn, look at this, if we burn 4.0 times 10 to 15 grams of octane, how many grams of CO2? This is mass to mass, all right? This is mass to mass. Stoichiometry is one of the longest, by the way. So how you will set up that is, and by the way, you need to be well rounded with analog calculator, because this is what you'll be using. You should be able to key in a number in scientific notation. So here is 5 grams of C8H18, right? This is the grams of fossil fuel octane times using the molar mass. You may be given, you may be required to find. This is 114.22 grams of C6H18. This is 1 mole of octane, C8H18. What I've done here is convert the grams to moles, grams of octane, and using the mole ratio between, between octane and CO2, which we are looking at, I want to cancel this and that so that we remain with moles. This is the mole ratio. Mole ratio here is mole of C8H18 moles of CO2. This is the mole ratio, by the way. For every 16 moles produced, 2 moles of octane must be consumed. You see how I'm canceling out that. And then the last conversion factor here is times the molar mass here. Molar mass of, we want to get rid of moles of CO2. This is grams of CO2. This is 44.01. Let's just use the periodic table. You are given right here, use the periodic table. If you are not given, equals to, using your calculator, this is adds. That means it adds 1.2 times 10 raised to 16 grams of CO2. This means it adds this amount of CO2 into what? Into the atmosphere, into the atmosphere. With this, you can see that two significant figures because of the two significant figures. You have to figure out, this is the molar mass of CO2, this is the mole ratio in the balanced equation, and this is the mass right here. We started with the mass, we ended up with the mass right here, so it is mass to mass. I have problems at the end of chapter. You can try 37, 39, and 41 as a practice to know that you can handle mass to mass stoichiometry, this is just revisiting the stoichiometry, the mole, which you know what it means, right? Mole is a unit of measurement used by chemists. I know you can determine the molar mass we looked at before, and maybe just look at the empirical formula later on. I'm just looking at this, the mole. The mole represents this number of objects, Avogadro number, 6.022, sometimes 223, it's the same thing. But here is just like some of the units you are familiar with. When we say a pair, that means you have two. A dozen means 12. A crossover pencil, that means 124, 144 pencil, and so forth. But what we need to learn is when we say 1 mole of a substance, that means you have Avogadro number. Let me just minimize this number here. And by the way, we use this Na, which is 6.022 times 10 raised to 23. This is called Avogadro's number, Avogadro's number. All right, Avogadro's number. So, and it represents 1 mole. So 1 mole is the same as that. All right. There is a mole day, which is 6:02 a.m. to 6:02 p.m. every October the 23rd. It's a mole day. We don't celebrate, but there is a day in honor of Amadeo Avogadro, who came up, and we use this symbol notation just to let you know. You'll see this, you may see this in the future. Na represent Avogadro number, which represent 1 mole of object. I've talked about mole to mole. What that means, we did this conversion before, mole to molecules, which I don't want to spend more time. I know we did this before, but you can revisit and see how you can use Avogadro number, relationship between atoms, molecules, and the mole, which we did before. Even molar mass, I know you can calculate, if not given, using the chemical formula. You can find the molar mass of a substance, and by the way, 1 mole of an element weighs atomic mass in grams. And it has Avogadro number, just so that you know. The numerical value you see on the periodic table represent the molar mass of a substance, and it contains 1 mole of substance, which means it has the Avogadro number of molecules. Avogadro number of molecules. This is something we did before, determining the molar mass. I know you can do that, but here, again, you should be able to convert. This is the roadmap. You may find it handy. Math is not something you read. You have to practice. So if I look at this roadmap, I don't need to memorize this. All I need to do to commit to my memory is practice problems at the end of the chapter, problems on Alex, until you know which conversion factor you need to generate in order to move from crumbs to moles, from moles to crumbs, and so forth. Please revisit this. You may just print this slide right here so that you use when you be completing your Alex assignment. This is just a setup to determine the number of moles of 10 grams, number of moles of carbon in 10 grams of natural occurring carbon, the mass of 0.905 moles of sodium chloride. Again, here, if you don't know the formula for sodium chloride, how will you determine the number of moles? You need to find the molar mass. So again, like I said, you should go back to chapter 3, learn how to write the correct chemical formulas. You know, it's assumed right now that you know how to write the chemical formulas for your compound. This is the sodium chloride. Using the periodic table, we are not given. This is the molar mass of sodium chloride, right? This is the molar mass of carbon using the periodic table. So these pieces of information, you can just set up your calculation. This is the number of moles. We have found. This is mole to mass. I mean mass to moles, by the way. Mass to moles using the molar mass, using the atomic mass and the molar mass. We call this molar mass, atomic mass. Yes, the molar mass of each one of them. It's the same thing here. You can read this on your own, how I've set up the problem in such a way that you can follow how you convert from grams to molecules using the Avogadro number. The other one was from moles to mass. You need to know where you are and what the question is asking. These are just problems. You can go back 43, 45, 47, 49, and 51 on page 162. It will give you good practice. I believe it will give you solid foundation on stoichiometry. Like I said, math, you don't read math, you need to practice, all right? You need to practice. That marks the end of chapter 4, part A. I'll come back again in part B so that, we continue. Other than that, thank you.